of another talk of the Rich Seminar series. Before we start Philip's talk and I introduce Philip, I'd like to announce the rules for today. The talk is being recorded and being put online later on. The questions are not being recorded, so we will switch off the recording after Philip's talk. Also, please, for securing some bandwidth, and for those that haven't got really a good bandwidth, please switch off your videos during the talk. I will keep mine on so Philip has something to look at, even if it's not very nice. And just switch your microphones off, please. During the questions, of course, we will do the usual principle of hand raising or typing into the chat, and then we will address the questions by order. Let me briefly introduce to you Philip, who's the classic example for a long-term commitment to IODP, I think. He started off his PhD in Erlangen in 2013 with Marcel Regulus and Carsten Haase working on an extensive IODP sample set before he moved on 2014-15 as an Alexander von Humboldt Fellow, Theodor Fellowship to the Australian National University in Canberra, working together with Richard Arculis, Oliver Nebel, and Hugh O'Neill. Before he came back to Germany for a very brief stay in Erlangen, I think it was no more than 2 months, if I remember correctly. And since 2016, he's a postdoctoral researcher, fixed term, unfortunately, in the Marine Mineral Resources Group of GEOMAR. He's also the German representative of Interrich, and he's had numerous German research vessel cruises, but I'd like to point out that he twice joined the famous joyless resolution and IODP leg 351, Isobornine Mariana's Arc, and the IODP leg 376 to the brothers Arc Flux. So he's a very experienced IODP participant and user of the samples, and I think this is what he will talk about today. And without further ado, Philip, the stage is all yours.
Okay. Thank you, Christoph, for a nice introduction. And of course, thank you very much for inviting me to this talk or to this seminar. Today, I would like to talk about how we can use petrology and geochemistry actually to advance our knowledge of the evolution of oceanic basins through scientific drilling. And before we dive straight into the science, I first would like to thank a series of people, of course, as Christoph pointed out, those where I did my PhD at the University of Erlangen-Nuremberg, and then, of course, the Australian National University, where I spent some time as a postdoctoral researcher. And then, of course, all the people I sailed with on IODP expeditions and later on worked with those on collaborative research projects. And in that respect, I particularly would like to thank the 2 IODP programs, the pre-successor, the Integrated Ocean Drilling Program, and then the International Ocean Discovery Program, and with the European part, the ECORD, European Consortium for Ocean Research Drilling, that provided me with the possibility to sail twice, and of course the core repositories in Bremen and at College Station that provided me with samples for doing or carrying out this science. Whoever already sailed on joyless resolutions knows about the capability of this really impressive ship. Even though it's quite old now, it's still exceptional what you can achieve with the drill rig, the moon pool that you can see here. Sorry, just changing here my pointer. The moon pool in the center of the ship, where the drill rig is then going down to the seafloor, that allows you to really get samples of the subsurface, sometimes several kilometers of rock, and certainly several kilometers of water depth deep down in the oceans. You can see down here kind of one of these re-entry funnels that illustrates the complexity of these operations in really open ocean waters. But still, the facilities, the laboratories on this boat are really exceptional and allow really to get rock samples, but then also to carry out really cutting-edge science that is related to the evolution of the ocean basins. However, the ocean drilling programs, they are running now for more than 50 years. And in these 50 years, the actual amount, the volume of recovered igneous rocks is rather small. So on this diagram, you can simply see a compilation of various drill sites versus the penetration depth into the igneous crust. So that can be volcanic crust, it can be the dike complex, gabbros, or then serpentinized peridotites, so mantle rocks. And total volume of those is rather small. So we can see the length is a little bit, or at least in 2012, that is, I think, one of the most recent compilations of this kind. You can see the total length was a little bit less than 6 kilometers of core altogether. And assuming then kind of a typical core diameter, that ends up to a little bit more than 1,000 cubic meters, which if you put it all together is a cube of just about 10 meters side length. So you can see that that's not very much of rock if you consider how vast or how big the oceans actually are. And that compared to the extensive sampling we do on land, it's really a small fraction where we have to do our science bit. So in that regard, the perspective of continuing scientific drilling to 2050 or even beyond is really, I think, quite exciting, and also will add a lot of important material to get more representative samples and more detailed insights into the geological processes that affect our oceans. So today, I want to talk about 3 different aspects that are related to the material from ocean drilling that we already have. I think this is quite valuable, that material, and that is related to the evolution of the ocean basins. You all know that new oceanic crust is continuously formed along mid-ocean ridges, and by drilling into the oceanic crust, we can get some insights into the stratigraphy of the oceanic crust, and by that not only understanding kind of the third dimension of the crust, but also looking into the timescales of the crustal accretion at mid-ocean ridges. If we then consider not only a single drill site, but look at different drill sites that are across oceanic basins, so that cover a full range over the evolution of these basins, we can get some estimates, or we can compare these sites and then study the compositional variation between those. And I will show you later that this really gives us some idea of the thermal evolution of these basins, or more to say about the thermal evolution of the upper mantle that is providing, or from which then these ocean basins are formed by partial melting. And last but not least, I will have a quick look at convergent margins, so places where ocean basins are consumed. And here we will have a look at the timescales of subduction initiation, the processes that are happening place when a new subduction zone starts, and how or why we also create kind of a new ocean basin at this moment. So 3 different examples, partially different settings, but overall it's all about the timescales of the geological processes that are preserved in these drill cores. So first of all, let's move on to the timescales of crustal accretion. So looking into the cross-section or into cross-sections of oceanic crust. And here in my talk, I will only focus on the volcanic layer. So let's say the upper 500 to 800 meters of the oceanic crust. From classic ophiolite models, previously it was assumed that the oceanic crust is rather uniform, has a simple structure. You can see the sediments on top, lavas, sheeted dike complex, and then the big plutonic sections with gabbros, and then the lithostrate part of the upper mantle. However, this uniform crustal structure is a little bit more complex in nature, and that is mainly a function of the spreading rate. So here we can see 2 simplified cross sections of a mid-ocean ridge, and one example for slow spreading here in the center, and on the right-hand side for fast spreading. And you can already see by just the first glance, they are quite different in morphology. For example, at slow spreading ridges, usually we have an axial valley, we have a lot of extension, a rather poor or low magma supply. Often only the segment centers are magmatically robust, meaning that they get enough melt supply to form a proper igneous crust, whereas at the segment ends, or where magma supply is very low in general, we can exhume mantle rocks that are then interacting with the seawater, of course, to serpentinize the peridotite. And in contrast, at fast spreading rates, we have commonly an axial high. So the crust is separating very fast, a lot of melt is produced, and that is meaning also a lot of magma supply at these locations. This magma does not only pond directly at the ridge axis, but can also flow further away where it then ponds. So here the melt can travel at the surface a little bit, but other than that, usually the melt injection is happening mainly at these lateral dikes that often can propagate along the ridge axis. However, a lot of other processes are affecting this fast spreading crust. We can have really long-living axial magma lenses in these systems that are then kind of episodically replenished by new batches of melt arriving from the mantle that are then mixing with previous batches of melt and partially crystallizing. And yeah, so apart from ophiolites, where of course some kind of oceanic crust is exhumed on land, ocean drilling is the only technique actually to study the third dimension of the oceanic crust in situ. So I think that's more representative than ophiolites, even though kind of the sampling is quite limited. But fortunately, if we look into kind of what we have drilled into the mid-ocean ridges, or in oceanic crust, better to say, we have a nice record. So here are two examples, two sites from the Atlantic Ocean. One is 80 million years old, the other 120 million years old. And you can still see these nice black glass rims on pillows in the drill core, or here on the electron microprobe, an image of unaltered glass 120 million years old from the Atlantic. So this record is really nice and unique and allow us really to study the composition of these melts that were erupted back in time or at various positions now in the crust. So kind of over the time frame of when the crust is accumulated on oceanic ridges. We have sampled about 45 drill sites in the Atlantic and the Pacific Ocean. From that, we got more than 500 unaltered glass analyses. These were done by electron probe for major elements and laser ablation for trace elements. And in this first part, looking more into the crustal processes, therefore plotted these sites drilled into the basement, so ignoring any overlying sediments or any overlying sediments. And those are plotted versus spreading rate, and that gives you a nice overview that even though there are only 4 or 5 oceanic drill cores that really were cored several hundred meters into the oceanic crust, at least those 4 to 5 cover quite a nice range of spreading rates that are representative for the spreading rates we observe today on our Earth. If we then look a little bit more into the chemistry, into the data, I plotted here simply MgO, which you can use as a measure of magmatic differentiation. So typically, if you extract melts from the mantle, they would have MgO between 11 and 14 weight%. So these are already, to a certain degree, fractionated from mantle melts. But still, some of them are quite common, more, not primitive, but parental melts to the morb that is later then erupted on the seafloor. And if you plot those versus basement depth, again, it's this plot is dominated by 4 to 5 drill cores. You can see here 417D is quite important, 504B, 801C, and 1256D in superfast spreading crust. So those are drill cores that were drilled 300 to 500 meters into the volcanic section of the oceanic crust. And you can see some trends in here. Hole 417D, for example, the sigmoidal shape up here, or then in superfast spring crust, these excursions to a very low MgO content. So there must have been an event where there was extensive fractional crystallization happening place. The problem by just plotting them versus depth in basement is that you still do not have any idea of how much time is preserved in these drill cores, because they have been formed, or the crust has been formed at very highly variable spreading rate. These 4 sites you can see from 40 millimeters per year to more than 200 millimeters a year. That's quite a lot, or quite a lot of variability. And so one of the key questions to us was then to understand actually how much time is preserved in these cores. And important to add that no conventional dating technique is possible to age date those samples. Probably the timescales are too small. For example, for Paleo you do not record any reversals, probably 1 if you are lucky. So that's not a good technique. There's not really a lot of potassium in these rocks, so argon dating is not really possible. And also, if you have a drill core that's 120 million years old, you cannot resolve a few thousand years time difference in these cores. So that's a major issue. And therefore, we tried to get some idea of the potential time by inventing, or not inventing, but creating these model stratigraphic ages for our drill cores. And these MSA, these ages are based on compiled data. So please do not go in all detail through this table, but I will guide you through the key information contained here. So there are different segments where we have information on the thickness of the volcanic layer. For example, the Planko, at the Planko transform, it's about 485 meters. We have information from this location about the width of the zone over which the oceanic crust is being accumulated. So it's somewhat similar to the neovolcanic zone, but it's not only the neovolcanic zone, it can include also zones where, for example, by off-axis volcanism or lava flows that travel away from the ridge axis, the crust is still being accumulated. And then with the information of the full spreading rate, we can calculate how much time actually it takes the crust, or how much time the crust is within this crustal accretion zone. That is here, this time CAZ in 1,000 years. And then by looking into the thickness of the volcanic section, you can get these general accumulation rates in meters per 1,000 years. But again, this only applies to the volcanic section of the oceanic crust. Yeah, these accumulation rates gives you a nice function of full spreading rate. Again, it's a very simplified model that is only depending on full spreading rate. But I think if you compare it, for example, to geophysical models on seismic crustal thickness or rare earth element inversion that was done by, I think, White et al., it shows quite a nice similar pattern that only at very slow spreading rates you get a very, very big variation, whereas then at faster spreading rates you get less variation, and that makes us somewhat confident that at least to a certain degree these ages are also meaningful. And then with the drill depth, because this rate is only a function of meters and the spreading rate, we have this information in the drill sites. We can convert the drill depth into an age information. We have done that mainly, well, we have done it for all the sites we sampled, but again, focusing on the 4 ones that cored several hundred meters. Here's just to show you one example, site 801C in the Pacific. It's one of the older sites in fast spreading crust. And if you look into kind of this classic, or one of the classic Harker diagrams, MgO plotted versus titanium, lower MgO meaning progressive magmatic differentiation. And just by this compiled data, you would assume there's a simple fractional crystallization trend, one liquid line of descent, how we call this. But if you put the depth into basement, or then the age on top of that, you can see it's not that simple. There are several episodes that you can relate that show some sort of magma recharge. So going to more primitive melt compositions, higher MgO, and then subsequent crystallization. In these 4 sites that I mentioned, we could identify in total 16 individual of those episodes. and then using the bulk geochemical composition, then also the mineral composition from phenocrysts that we analyzed in these glass samples. We can model the amount of crystallization and of course also the mineralizing assemblage by using a rather simple least squares fitting to the liquid line of descent. And I mentioned the important age information. So we can use these different episodes to look into the variation MGO. I mentioned that we modeled the mineral composition and the amount. That is then here the crystallization amount that we inferred from these differences in the liquid line of descent. And important is then really here adding the time information, because the volume or the amount of crystallization and the time we can then infer of how fast these melts have been crystallizing. Of course, that is only a minimum estimate. It can be much faster because we cannot be sure that we captured each of these intervals where magma is being replenished and then subsequently fractionating. However, from the data that we could extract from these drill cores, you see a nice function of related to, again, spreading rate. If you plot the crystallization rate for these sites, you can see that with faster spreading rates, not very much surprising, you see a tremendous increase of rate of crystallization. And this mimics somewhat also what we see or what we know from the depth of the melt lenses in these systems, again, function of full spreading rate, and gives us some idea of fast spreading rates. We have shallow melt lenses, faster crystallization, and that's probably providing a lot of energy for hydrothermal convection. And this may also explain why we see in these samples, not only in these, but in more general, also this trend in chlorine over potassium versus the full spreading rate. Again, in red here, Atlantic sites in general, blue Pacific, and these 4 to 5 drill sites or drill cores that we pointed out. And you see that there's a positive correlation between those that can be either related to the direct assimilation of a hydrothermal brine or the indirect assimilation of hydrothermal products by assimilating hydrothermally altered oceanic crust. Going on a more general view, if we look into kind of these timescales that are preserved in these drill cores and looking simply at the chemical variability that is also preserved in these drill cores, not only these drill cores, we compiled more data on single lava flows. There's, for example, the 96 eruption at the North Gorda segment. Laki is contained in here eruptive units. So those are eruptions that were measured at or compiled from the active ridges, and then full drill cores, and then whole transects. There are 3 nice transects across the East Pacific Rise, limiting to the neovolcanic zone, or then the full transect that cover almost 1 million years of crustal evolution. And then what we observed here is, of course, again, not very surprising, the MGO, that with longer time periods that you look at, you see a high variability. So that is not, or that is the variability in MGO. So it's not a absolute number, it's the variability pointed out here. But what is more surprising is that you also see a systematic offset between this lower spreading ridges here in red and fast spreading ridges then here in blue. And that can be, or one pattern can be or related to the magmatic differentiation, but the same is also true here if you look at incompatible element ratios that can be or can reflect to a certain degree also magma mantle source heterogeneity. So this might be a second effect that affects the composition of the drill cores, and there it's always important to look at the timescales you're sampling. So that's how we ended up with looking at not only at the processes that take place at a mid-ocean ridge, but also the timescales. First, briefly looking at the processes. So we know, of course, that the upper mantle is not homogeneous. It's a highly heterogeneous mantle source from which we extract these primitive melts. Then what is very important is also the mode, how we extract these melts. It can be porous flow or channel flow. Then probably these melts are already crystallizing in a polybaric way during the melt ascent through the lithosphere. before they then ponding in axial meltlands if present. There they can be replenished in several events, crystallizing, tapping different portions, and so on. And then further complications, the assimilation, interaction with the crust, and of course then how the crust itself is accumulated here at the mid-ocean ridge on top. What we found out or compiled in terms of the time scales, the mantle source composition, that might be rather long-term changes, probably hundreds of thousands years or even millions of years. The melting subtraction from used areas is rather fast. It can be up to meters per year. But then the physical conditions of the macroplumbing system, as we could have seen in the chemical variability in timescales, that's already quite short, or even shorter, tens to hundreds of thousand years. Recharge events can be very short, tens to hundreds of years. We know, for example, from the East Pacific rise, there was certainly one event taking place within 14 years. And then the eruption frequency that we can also infer partially from this study and other data on slow spreading, that can be 1 per 1 to 10,000 years, whereas the fast spreading ridges eruption frequency can be 1 per 5 to 100 years. With that, I would like to conclude from this part on really the crustal cross sections and looking now more into the long-term evolution of oceanic basins. So comparing distinct drill sites. And the idea behind why we were aiming at doing this is that there's a concept of continental insulation, meaning that if we have an open ocean, the cooling of the crust is quite efficient, and it allows to extract the heat that is being generated in the Earth's mantle. Whereas during times when we had, for example, supercontinents covering this part of the upper mantle, we limit heat transfer to conductive heat transfer, which is far less efficient. We had a thick lithospheric lid on top, leading to insulation of the upper mantle. And we wanted to test this, or we aimed at testing this by looking whether we see a change in the chemical composition of MORB after breakup of large ocean basins. And to do this, you first need to kind of change your perspective at how you look at ages. So this time, what relates to this delta age concept. So we are not looking at absolute ages. So if you look, for example, here at a mid-ocean ridge, and this ocean ridge is part of a propagating ocean basin, so progressive rifting is taking place. You can have two drill sites. The absolute age would be 40 million years in this example. However, if you turn your perspective and you're not looking from the zero age, so from the mid-ocean ridge, but you're looking from the rifted margin, so how much time has passed since this ocean basin broke up. And if you compare these two sites do not have the same age, but this site here, for example, has erupted or formed only 10 million years after rifting or oceanic breakup has been taking place at this location. Whereas if you go along flow lines and looking further down here, breakup was far further back in time, time of breakup 100 million years, so the delta age, the time difference between breakup and eruption at this site would have been only 60 million years. You can do this at zero age. A nice example would be the Red Sea and the Indian Ocean. So rifting in the southern Red Sea only about 8 to 50 million years ago. But then if you go to the central Indian Ridge, the northern part, 90 million years, when rifting has started in this region. The southern central Indian Ridge, 150 million years, and then the southwest Indian Ridge, southeast Indian Ridge. Here we had about 150 million years ago. And then we used geochemistry to infer the temperatures and use that to constrain mantle temperatures. The nice thing about the geochemistry, if you want to look at these systematics, is that first of all, you observe a global correlation between sodium content. And the sodium content needs to be corrected for effects of fractional crystallization. In this case, we corrected it to magnesium of 8 to 8%. And the sodium is an incompatible element and is therefore commonly used as an indicator for the degree of partial melting of the upper mantle. And what you see on this diagram is then this indicator, sodium 8, plotted versus ridge depth. And you can see this nice correlation that really the water depth of mid-ocean ridges is correlating, of course, in a simplified way to the average degree of partial melting in the upper mantle. And if we take this example from the Red Sea and the Indian Ocean, looking at the same systematic, so sodium-8 plotted versus water depth, in these hexagons, you can see again the global correlation, but then you can see here in the red outline, it's the data for the Red Sea, the northern central Indian Ocean ridge, the southern central Indian Ocean ridge, and then the other Indian Ocean ridges. You can see that obviously depending on the setting, how long rifting or breakup has taken place at this location, you can see that also with the longer time has passed since the breakup, you get greater water depths and higher sodium-8 contents, indicating lower degrees of partial melting. And we compared that again to these 45 sites we sampled in the Atlantic and Pacific Ocean. So here you can see a global map of these drill sites. The colored color codes here in the ocean, of course, corresponds to the age of the oceanic crust. You can see here in the Atlantic, these sites we sampled, and here in the Pacific. And again, these drill sites, you are familiar with some of them already, plotted this time not against spreading rate, but with the absolute age of the basement that we use for comparison. And then I mentioned sodium-8 is one indicator for degree of partial melting. It needs to be fractionation corrected. It still does not give you a primary melt composition, but you can approximate these melt compositions by first correcting using general equations for correcting for the effects of fractional crystallization. That's what we did only for samples with MgO greater than 7 weight percent. Then we corrected to MgO of about 8.5 weight percent. That is because at this point it's assumed that only olivine is the only fractionating phase in these systems. But then we used equilibrium olivine with these glass compositions and added those in incremental steps until our melt is in equilibrium with mantle olivine. So assuming that at this point our melt is in equilibrium with the upper mantle, indicating then a composition that could have been formed in the mantle. And then there are different ways how to convert these chemical compositions into potential temperatures. You can use sodium, iron, or magnesium. You can see these publications that we used of the primary melt. That gives you temperatures that we, of course, also apply to zero mid-ocean ridge basalt data that we compiled from PETIB and the Smithsonian Abyssal Volcanic Glass data file, ending up to almost 10,000 samples of the present ocean. And you can see these different temperatures, Atlantic and Indian Ocean in red, and blue for the Pacific, slightly different, but overall quite similar. So that makes us quite confident that we can use these temperatures or the chemical composition to calculate temperatures. And then finally, to compare the history of the Pacific and the Atlantic Oceans, it's important to also take into account Paleo Geography. So if you look at this place, you can see that the Atlantic, the Central Atlantic at least, breakup took place at around 180 million years ago, whereas the oldest site preserved in Pacific crust, 801C, that is about 170 million years old. And this site formed at least 2,000 kilometers away from the nearest margin. So that's quite a difference, whether you had continents surrounding your newly forming ocean basins or you are already in open ocean setting. And that's is leading us to the mantle potential temperature estimates. Again, using here only the example of sodium, plotted here versus delta H. So keep in mind, 0 would be time of breakup, then going back to more time since breakup to get rid of the relative timing of breakup at different locations. You are familiar with this data, the Red Sea data, Gulf of Aden, Central Indian ridges, Southwest Indian ridges. You can see already kind of this overall decline with more time since breakup. We compared this with the relative frequency of 0H mob, which is illustrated by this histogram here for the Atlantic and Indian Oceans. calculate the median temperature and also the variability in 1 sigma, and put on top then our data from these ancient drill cores, or the drill cores are recent, but the crust they drilled is ancient. And what we see is that about 50 to 100 million years after breakup, we record higher mantle temperatures in these drill cores, which led us to the conclusion that we really observe higher mantle temperatures following this rifting event, and that this is related really to this effect of continental insolation. There's further geophysical evidence for that. Several nice studies by Cortese and co-workers who used numerical modeling to look into this issue. So if you have here a continent cover illustrated here by this black lid on top here, they calculated that this effect would result in differences in potential mantle temperatures of 100 or even in extreme case to 150 degrees Celsius or Kelvin. Then there's other evidence. If you look, for example, at the morphology of the seafloor, if you have higher temperatures, faster spreading, you create a more smooth surface of the oceanic crust. There's lower melt supply, lower temperatures result in more rough topography. And what we see here in this seafloor roughness, it's a study by Whittaker et al. They also observe a similar temperature anomaly that persisted up to 100 million years after breakup. And last but not least, there's also really seismic evidence for crustal thickness. Nice study by Van Avendonk et al. 2016 that compared the 3 oceanic basins, and what they found is also that the crustal thickness was about 1.7 kilometers greater in the initial phase of breakup after the breakup of Pangea. Sorry. Last but not least, a short section where I want to look into how we can destroy oceanic basins. So looking into the timescales of subduction initiation, quite contrary to a ridge seminar, but I will show you in a minute why it's still related to ridges and why we are forming new ridges or new oceanic crust when we consume large oceanic basins. So there are different ways actually, or different theories how we think we can start a new subduction zone. I don't want to go into detail or too much detail into that. I can just refer to this nice summary paper by Arculus et al. In 2019. But with respect to the IOTP expedition 351 I was sailing on, we're looking into the Isobornine Mariana arc system. And here we're talking about spontaneous or hybrid induced spontaneous subduction initiation process. Doesn't mean, or we do not have to go too much into detail what that actually means. But both ways are that a transform is kind of collapsing, so spontaneously or with some external forces like a change in plate motions results in the sinking of the slab, and then this space of course has to be filled by new crust. It comes to decompression melting, and we get what is now called proto-arc spreading in these systems. And so far all the information we had on this issue was from the fore-arc. And so in 2014, a series of IODP expeditions targeted this topic, not only looking into the fore-arc, but also getting a drilling perspective from the rear arc. And that's where we went. So this is a map of the Isobornine and Mariana arc systems in the Western Pacific. We can see now the kind of active arc front. And then you have several remnant ridges, very nicely to see here in the Marianas, where a few million years ago, the Mariana back arc opened and leaving behind this remnant arc, the West Mariana Ridge. And the same has happened about 25 million years ago. So we have this remnant Kyushu Paleo Ridge, which is assumed the proto-Isobornine Marianas arc ridge, which is now separated from the active arc front by the Shikoku Basin and the Paris-Vela Basin. And so there was this nice piece of oceanic crust that was supposed to predate subduction initiation in this area. That was the target by this IODP expedition. It was a very challenging expedition, but it was very successful. So drilling took place. You can see here there's nice column here for scale that shows this resolution on top. So drilling took place in 4,700 meters water depth, but we still managed to drill a further 1.6 kilometers into the crust recovering this nice record. So this is kind of a composite core image. Of course, on top we had hemipelagic mud, kind of background sedimentation, but then we recovered the late stage of the arc in Unit 2. We recovered almost 1 kilometer of nice volcanic clastic turbidites derived from the adjacent proto-Isobornine arc. And then more interesting, some record of the very first glimpse of arc volcanism here in this Unit 4. And most importantly, 150 meters of igneous basement that is predating subduction or island arc magmatism in this region. There's a series of papers that derived from this expedition, but really the important part here is, again, these sediments provide a very nice age control by biostratigraphy, by paleomagnetism, but also by radiometric dating, also of the igneous crust below. And the interesting part of that is that this oceanic igneous crust, it's distinct from those that is formed at mid-ocean ridges, back arc basin, or at island arcs. So plotting here silica versus titanium, can see the Philippine Sea plate field here is the study by Ishizuka et al. 2018, and all the samples we recovered during this expedition. And we can see in terms of chemical composition, it's quite similar to 4-arc basalt, with some evidence probably to some influence by the subduction zone itself. So these are distinct compared to normal mid-ocean ridges. They're all special to back arc basins. And the special thing about this crust is that these have been transferred rapidly from mantle depths. They preserve the subcrustal mineralogy and are almost unaffected by the typical replenishment tapped crystallization processes of mid-ocean ridges. So putting that together in terms of the age, what we know from the Isobornine 4-arc, that's a compilation by Ishizuka et al. 2014, and that's the record from this site. The ages are similar, even though probably slightly younger on the rear arc, but that led to really the reconstruction of how subduction or this proto-arc crust has been forming. So the slab was sinking. The total basin width is at least 300 kilometers, and the time we have available for forming this part of the crust is only 3.3 million years. So if you consider this, then the spreading rates at this time must have been very high, depending on how the spreading ridge has been, the symmetry of the spreading ridge, whether it's symmetric and has been intermediate to fast, whereas if spreading was asymmetric, which we think is more likely because of this age difference that we observe, then we have really fast spreading rates up to 150 millimeters per year in this setting. And important to point out that by this drilling, we do not only have this nice record of subduction initiation, but really also then a nice subsequent record of evolution of the first glimpse of arc volcanism, the arc building stage, and then also finally how the arc changed, or sedimentation at least changed, the volcanic clastic sediments, the supply changed before rifting of the back arc in this region. So to sum up, ocean drilling allows really to directly sampling the subsurface and old in situ crusts. I think that's really unique to any geophysical models or any crust that is exposed on land. And these IODP core repositories are really an invaluable sample archive for this. So it does not have to be always a new expedition. In these archives, there's a lot of material that still needs to be looked at. We can use individual drill sites to look into the lithostratigraphy of the oceanic crust, but also to infer the timescales of magmatic differentiation at mid-ocean ridges. And we can use the basalt geochemistry to look then into the evolution across ocean basins, especially into how the thermal evolution of these ocean basins changes. And we found some evidence that really insolation of the upper mantle by supercontinents has an important thermal effect on the mantle itself. Last but not least, ocean drilling at convergent margins then provide really evidence for the processes and the timescales of the subduction initiation. And as I pointed out, but haven't shown today, then the subsequent arc inception and evolution. With that, I would like to thank you for your attention, and feel free to ask questions. Let's look forward to an interesting discussion.